Howdy! This is O-REU Project Overview, Early Detection of COVID-19 Using Wearable Thermal Energy Harvesters, created by Brian CARPMAN with help from his research advisor, Dr. Chung-Ho Yu. Who am I? I'm Brian CARPMAN. I'm an undergraduate student at Texas A&M University, class of 2022, and I'm also a material science and engineering major. But I'm also a maker. I love to build things and I love to tinker. Who's my advisor? My advisor is Dr. Chung-Ho Yu. His research topics include fun things like soft robotics, energy storage, energy conversion, water desalination, and, important for this presentation, thermal energy harvesting. So, our program sponsor is the National Science Foundation. So the problem, the SARS-CoV-2 virus. It's also more commonly known as COVID-19. It's declared a public health emergency of international concern in late January. It's kind of been wreaking havoc on society ever since, and the end game for this outbreak is a vaccine. However, the vaccine is not going to be available for a considerable amount of time, at least multiple more months. And we've been using other stopgap measures in the meantime, such as social distancing, extensive and fast testing, and contact tracing. However, the virus gives us difficulties in these areas with a long incubation period, possible asymptomatic carriers, and very common initial symptoms. So our current screening methods are mostly screening for temperature, because a fever is one of the most common symptoms of the virus. But this usually means tedious screenings at like the entrance to a building, and you only get one piece of data. And it only detects fevers above a certain threshold. So what if instead we could have a trend of a person's temperature over time? And what if we could detect the fever just by the curve before we could detect it from just the temperature? Because if we look at this diagram on the side, we can see that fevers often have very weird curves compared to your normal body temperature. And what if we could power the temperature sensor with just your body heat? So, wearable temperature sensor. Powered by a thermally charged supercapacitor, using the Surrey effect, and capable of transmitting and storing data, and preferably no batteries to make this even thinner and lighter. So, some software that we used. We used ANSYS for the thermal simulation of the device, and we used a little bit of multisim for electrical simulation. So, one of the most obvious things from the thermal simulation is that the ambient temperature has a very large impact on the delta T. And we can see this by this one where you have an ambient temperature of 22°C versus this one where you have an ambient temperature of 32°C. We have a delta T on the 22 of about 3 degrees, and we have a delta T of the 32 of about 1 degree. So the effective temperature. Our device is basically a heat engine. And so heat engines usually gain efficiency with greater temperature gradients, and the Surrey effect also scales with delta T. So what's the Surrey effect? It's also known as thermophoresis. Basically the idea that different types of particles react differently to a temperature gradient, and that we can push some particles along a temperature gradient. This can be seen in this little diagram by how the particles preferentially go down the cold side and not the hot side. So, a background. So we're going to be using sulfate intercalated graphene oxide films as the insulator/dielectric part of our supercapacitor. Then we're going to hit that with a laser to make laser-reduced graphene oxide to make our electrodes, but they're that part of the supercapacitor. And basically we're going to be using the movement of protons in the sulfate ions in the SGO so we can make electricity using the Surrey effect, because electricity is just the movement of electrons. So, some specs. So our TCSC produces a potential of about 9 millivolts per Kelvin, which doesn't sound like too much, but it's much better than a conventional Seebeck effect device, which only produces about 0.01 to 0.1 millivolts per Kelvin. This graph right here shows the voltage that we get from temperature differences, and it's for one with 8 modules in series. So we also found that heat sinks will also increase our delta T quite a bit, so we'll probably be using heat sink in our design. So we can see from this one that we get a delta T of almost 5 using the large heatsink, when we only get a delta T of about 3 using no heatsink. So, a bit of thermal design considerations. The heat flow needs to go actually through the film. And there's a problem, because this means that the film has to stand perpendicularly, but films don't like to stand perpendicular. They like to flop over like this paper. So we need something to support that. And also, we could really use a heatsink to increase delta T. So, here's my current thermal design. We got an aluminum extrusion on top. It's pretty cheap. It's basically a tiny little heatsink. Then we got polystyrene foam in the middle to act as a thermal insulator and force heat to move through the TCSC film. And we got aluminum plate on the bottom to help spread the heat to the TCSC. We can see that this works pretty well because we get a delta T of a bit over 3 Kelvin, and we can see that most of the heat gradient is in that middle part where the insulator is. So we can see that most of the heat is being forced through the TCSC. So what's our power budget? So our power budget is going to be based on a body temperature of 36.5 degrees Celsius, an ambient temperature of 22 degrees Celsius, which is about room temperature, and this gives us a delta T of a bit over 3 Kelvin. So the power output at 3 Kelvin is about 0.137 watts per square meter, and our TCSC surface area is about 32 square centimeters. So we get a power output of about 4.4 microwatts. Doesn't sound like a lot. And we get a voltage of about 1.728 volts. We get this by having 2 banks of 16 modulars in series. And this voltage is about equal to a coin cell. So, the device electronics. This device needs a temperature sensor to actually take the temperature, communication system to offload data, non-volatile storage to store that data, and a microcontroller to run the whole show. But it has some constraints. First, obviously, we have an extremely low power consumption because we're making 4.4 microwatts. It needs to be fairly cheap because this thing needs to be pretty mass producible, and it needs to be pretty small so it's not too bulky. So for our communication system, we decided on NFC because it requires basically no power. The readers are very common. They're even in phones these days. Our use case is pretty close to another case which uses an NFC, which is cold chain logistics. And the energy harvesting from the NFC we can actually use to top off the supercapacitor. So we decided for the microcontroller to use the AS39513 because it has very low power usage. It's got an onboard EEPROM, it's an onboard temperature sensor, it's got NFC energy harvesting, and onboard NFC electronics, and an onboard real-time clock so we can get timestamps on all of our readings. So temperature sensor, we're just going to be using the onboard temperature sensor that's on the microcontroller. And we're going to get negative 20C to 55C range, and we can actually change this range to a smaller range so we can get better precision. And we can do it 0.5C accuracy. And we have a logging time of 16 milliseconds, and a logging current usage of 166 microamps. So, an overview of the device specs. We can hold up to a week of readings taken once every 15 minutes. We use on average 4.2 microwatts of average power usage. And we cost about $2 for the chip and the flexible PCB. We don't know how much the actual thermal generator is going to cost. At least I don't. So here's the block diagram of the actual MCU. You can see that we're going to be using basically everything on this microcontroller except for the external sensor input and the SPI chip. Now for a conclusion. So, in conclusion, the application of a Surrey effect TCSC as a power source for a wearable temperature sensor is viable, and the ultra-low power electronics that are required for this application already exist and can be bought for pretty cheap. But real-world testing still needs to be done to determine if the application is actually practical. Thank you to my mentor, Dr. Chung-Ho Yu, the O-REU program, and Texas A&M University for giving me this wonderful opportunity for some undergraduate research. Here's some citations. Here's some image credits. Have a nice day. Thank you for watching.